small mammals isn't surprising, because there are literally thousands of wild species as candidates, and because they were of too little value to traditional societies to warrant the effort of raising them. But big mammal domestication virtually ended 4,500 years ago. By then, all of the world's 148 candidate big species must have been tested innumerable times, with the result that only a few passed the test and no other suitable ones remained. Still, a fourth line of evidence that some mammal species are much more suitable than others is provided by the repeated independent domestications of the same species. Genetic evidence based on the portions of our genetic material known as mitochondrial DNA recently confirmed, as had long been suspected, that humped cattle of India and humpless European cattle were derived from two separate populations of wild ancestral cattle that had diverged hundreds of thousands of years ago. That is, Indian peoples domesticated the local Indian subspecies of wild aurochs, Southwest Asians independently domesticated their own Southwest Asian subspecies of aurochs, and North Africans may have independently domesticated the North African aurochs. Similarly, wolves were independently domesticated to become dogs in the Americas and probably in several different parts of Eurasia, including China and Southwest Asia. Modern pigs are derived from independent sequences of domestication in China, Western Eurasia, and possibly other areas as well. These examples re-emphasize that the same few suitable wild species attracted the attention of many different human societies. In all, of the world's 148 big wild terrestrial herbivorous mammals, the candidates for domestication, only 14 passed the test. Why did the other 134 species fail? To which conditions was Francis Galton referring when he spoke of those other species as destined to perpetual wildness? The answer follows from the Anna Karenina principle. To be domesticated, a candidate wild species must possess many different characteristics. Lack of any single required characteristic dooms efforts at domestication, just as it dooms efforts at building a happy marriage. Playing marriage counselor to the zebra-human couple and other ill-sorted pairs, we can recognize at least 6 groups of reasons for failed domestication. Diet. Every time that an animal eats a plant or another animal, the conversion of food biomass into the consumer's biomass involves an efficiency of much less than 100%, typically around 10%. That is, it takes around 10,000 pounds of corn to grow a 1,000-pound cow. If instead you want to grow 1,000 pounds of carnivore, you have to feed it 10,000 pounds of herbivore grown on 100,000 pounds of corn. Even among herbivores and omnivores, many species, like koalas, are too finicky in their plant preferences to recommend themselves as farm animals. As a result of this fundamental inefficiency, no mammalian carnivore has ever been domesticated for food. No, it's not because its meat would be tough or tasteless. We eat carnivorous wild fish all the time, and I can personally attest to the delicious flavor of lion burger. The nearest thing to an exception is the dog, originally domesticated as a sentinel and hunting companion, but breeds of dogs were developed and raised for food in Aztec Mexico, Polynesia, and ancient China. However, regular dog eating has been a last resort of meat-deprived human societies. The Aztecs had no other domestic mammal, and the Polynesians and ancient Chinese had only pigs and dogs. Human societies blessed with domestic herbivorous mammals have not bothered to eat dogs, except as an uncommon delicacy, as in parts of Southeast Asia today. In addition, dogs are not strict carnivores, but omnivores. If you are so naive as to think that your beloved pet dog is really a meat eater, just read the list of ingredients on your bag of dog food. The dogs that the Aztecs and Polynesians reared for food were efficiently fattened on vegetables and garbage. Growth rate. To be worth keeping, domesticates must also grow quickly. That eliminates gorillas and elephants, even though they are vegetarians with admirably non-finicky food preferences and represent a lot of meat. What would-be gorilla or elephant rancher would wait 15 years for his herd to reach adult size? Modern Asians who want work elephants find it much cheaper to capture them in the wild and tame them. Problems of captive breeding. We humans don't like to have sex under the watchful eyes of others. Some potentially valuable animal species don't like to either. That's what derailed attempts to domesticate cheetahs, the swiftest of all land animals, despite our strong motivation to do so for thousands of years. Tame cheetahs were prized by ancient Egyptians and Assyrians and modern Indians as hunting animals infinitely superior to dogs. One Mughal emperor of India kept a stable of 1,000 cheetahs. But despite those large investments that many wealthy princes made, all of their cheetahs were tamed ones caught in the wild. The prince's efforts to breed cheetahs in captivity failed, and not until 1960 did even biologists in modern zoos achieve their first successful cheetah birth. In the wild, several cheetah brothers chase a female for several days, and that rough courtship over large distances seems to be required to get the female to ovulate or to become sexually receptive. Cheetahs usually refuse to carry out that elaborate courtship ritual inside a cage. A similar problem has frustrated schemes to breed the vicuña, an Andean wild camel whose wool is prized as the finest and lightest of any animals. The ancient Incas obtained vicuña wool by driving wild vicuñas into corrals, shearing them, and then releasing them alive. Modern merchants wanting this luxury wool have had to resort either to the same method or simply to killing wild vicuñas. Despite strong incentives of money and prestige, all attempts to breed vicuñas for wool production in captivity have failed, for reasons that include vicuña's long and elaborate courtship ritual before mating, a ritual inhibited in captivity, male vicuña's fierce intolerance of each other, and their requirement for both a year-round feeding territory and a separate year-round sleeping territory. Nasty disposition. Naturally, almost any mammal species that is sufficiently large is capable of killing a human. People have been killed by pigs, horses, camels, and cattle. Nevertheless, some large animals have much nastier dispositions and are more incurably dangerous than are others. Tendencies to kill humans have disqualified many otherwise seemingly ideal candidates for domestication. An obvious example is the grizzly bear. Bear meat is an expensive delicacy. Grizzlies weigh up to 1,700 pounds. They are mainly vegetarians, though also formidable hunters. Their vegetable diet is very broad. They thrive on human garbage, thereby creating big problems in Yellowstone and Glacier National Parks. And they grow relatively fast. If they would behave themselves in captivity, grizzlies would be a fabulous meat production animal. The Ainu people of Japan made the experiment by routinely rearing grizzly cubs as part of a ritual. For understandable reasons, though, the Ainu found it prudent to kill and eat the cubs at the age of 1 year. Keeping grizzly bears for longer would be suicidal. I am not aware of any adult that has been tamed. Another otherwise suitable candidate that disqualifies itself for equally obvious reasons is the African buffalo. It grows quickly up to a weight of a ton and lives in herds that have a well-developed dominance hierarchy, a trait whose virtues will be discussed below. But the African buffalo is considered the most dangerous and unpredictable large mammal of Africa. Anyone insane enough to try to domesticate it either died in the effort or was forced to kill the buffalo before it got too big and nasty. Similarly, hippos, as 4-ton vegetarians, would be great barnyard animals if they weren't so dangerous. They kill more people each year than do any other African mammals, including even lions. Few people would be surprised at the disqualification of those notoriously ferocious candidates, but there are other candidates whose dangers are not so well known. For instance, the 8 species of wild equids, horses and their relatives, vary greatly in disposition, even though all 8 are genetically so close to each other that they will interbreed and produce healthy, though usually sterile, offspring. 2 of them, the horse and the North African ass, ancestor of the donkey, were successfully domesticated. Closely related to the North African ass is the Asiatic ass, also known as the onager. Since its homeland includes the Fertile Crescent, the cradle of Western civilization and animal domestication, ancient peoples must have experimented extensively with onagers. We know from Sumerian and later depictions that onagers were regularly hunted, as well as captured and hybridized with donkeys and horses. Some ancient depictions of horse-like animals used for riding or for pulling carts may refer to onagers. However, all writers about them, from Romans to modern zookeepers, decry their irascible temper and their nasty habit of biting people. As a result, although similar in other respects to ancestral donkeys, onagers have never been domesticated. Africa's 4 species of zebras are even worse. Efforts at domestication went as far as hitching them to carts. They were tried out as draft animals in 19th century South Africa, and the eccentric Lord Walter Rothschild drove through the streets of London in a carriage pulled by zebras. Alas, zebras become impossibly dangerous as they grow older. That's not to deny that many individual horses are also nasty, but zebras and onagers are much more uniformly so. Zebras have the unpleasant habit of biting a person and not letting go. They thereby injure even more American zookeepers each year than do tigers. Zebras are also virtually impossible to lasso with a rope, even for cowboys who win rodeo championships by lassoing horses, because of their unfailing ability to watch the rope noose fly toward them and then to duck their head out of the way. Hence it has rarely, if ever, been possible to saddle or ride a zebra, and South Africans' enthusiasm for their domestication waned. Unpredictably aggressive behavior on the part of a large and potentially dangerous mammal is also part of the reason why the initially so promising modern experiments in domesticating elk and eland have not been more successful. Tendency to panic. Big mammalian herbivore species react to danger from predators or humans in different ways. Some species are nervous, fast, and programmed for instant flight when they perceive a threat. Other species are slower, less nervous, seek protection in herds, stand their ground when threatened, and don't run until necessary. Most species of deer and antelope, with the conspicuous exception of reindeer, are of the former type, while sheep and goats are of the latter. Naturally, the nervous species are difficult to keep in captivity. If put into an enclosure, they are likely to panic, and either die of shock or batter themselves to death against the fence in their attempts to escape. That's true, for example, of gazelles, which for thousands of years were the most frequently hunted game species in some parts of the Fertile Crescent. There is no mammal species that the first settled peoples of that area had more opportunity to domesticate than gazelles. But no gazelle species has ever been domesticated. Just imagine trying to herd an animal that bolts, blindly bashes itself against walls, can leap up to nearly 30 feet, and can run at a speed of 50 miles an hour. Social structure. Almost all species of domesticated large mammals prove to be ones whose wild ancestors share 3 social characteristics. They live in herds, they maintain a well-developed dominance hierarchy among herd members, and the herds occupy overlapping home ranges rather than mutually exclusive territories. For example, herds of wild horses consist of 1 stallion, up to half a dozen mares, and their foals. Mare A is dominant over mares B, C, D, and E. Mare B is submissive to A, but dominant over C, D, and E. C is submissive to B and A, but dominant over D and E, and so on. When the herd is on the move, its members maintain a stereotyped order. In the rear, the stallion. In the front, the top-ranking female, followed by her foals in order of age, with the youngest first. And behind her, the other mares in order of rank, each followed by her foals in order of age. In that way, many adults can coexist in the herd without constant fighting and with each knowing its rank. That social structure is ideal for domestication because humans, in effect, take over the dominance hierarchy. Domestic horses of a pack line follow the human leader as they would normally follow the top-ranking female. Herds or packs of sheep, goats, cows, and ancestral dogs, wolves, have a similar hierarchy. As young animals grow up in such a herd, they imprint on the animals that they regularly see nearby. Under wild conditions, those are members of their own species, but captive young herd animals also see humans nearby and imprint on humans as well. Such social animals lend themselves to herding. Since they are tolerant of each other, they can be bunched up. Since they instinctively follow a dominant leader and will imprint on humans as that leader, they can readily be driven by a shepherd or sheepdog. Herd animals do well when penned in crowded conditions because they are accustomed to living in densely packed groups in the wild. In contrast, members of most solitary territorial animal species cannot be herded. They do not tolerate each other, they do not imprint on humans, and they are not instinctively submissive. Whoever saw a line of cats, solitary and territorial in the wild, following a human or allowing themselves to be herded by a human? Every cat lover knows that cats are not submissive to humans in the way dogs instinctively are. Cats and ferrets are the sole territorial mammal species that were domesticated, because our motive for doing so was not to herd them in large groups raised for food, but to keep them as solitary hunters or pets. While most solitary territorial species thus haven't been domesticated, it's not conversely the case that most herd species can be domesticated. Most can't, for one of several additional reasons. First, herds of many species don't have overlapping home ranges, but instead maintain exclusive territories against other herds. It's no more possible to pen two such herds together than to pen two males of a solitary species. Second, many species that live in herds for part of the year are territorial in the breeding season, when they fight and do not tolerate each other's presence. That's true of most deer and antelope species, again with the exception of reindeer, and it's one of the main factors that has disqualified all the social antelope species for which Africa is famous from being domesticated. While one's first association to African antelope is vast, dense herds spreading across the horizon, in fact, the males of those herds space themselves into territories and fight fiercely with each other when breeding. Hence, those antelope cannot be maintained in crowded enclosures in captivity, as can sheep or goats or cattle. Territorial behavior similarly combines with a fierce disposition and a slow growth rate to banish rhinos from the farmyard. Finally, many herd species, including again most deer and antelope, do not have a well-defined dominance hierarchy and are not instinctively prepared to become imprinted on a dominant leader, hence to become misimprinted on humans. As a result, though many deer and antelope species have been tamed, think of all those true Bambi stories, one never sees such tame deer and antelope driven in herds like sheep. That problem also derailed domestication of North American bighorn sheep, which belong to the same genus as Asiatic mouflon sheep, ancestor of our domestic sheep. Bighorn sheep are suitable to us and similar to mouflons in most respects, except a crucial one. They lack the mouflon's stereotypical behavior, whereby some individuals behave submissively toward other individuals whose dominance they acknowledge. Spacious skies and tilted axes. Why did food production spread at different rates on different continents? On a map of the world, compare the shapes and orientations of the continents. You'll be struck by an obvious difference. The Americas span a much greater distance north to south, 9,000 miles, than east to west. Only 3,000 miles at the widest, narrowing to a mere 40 miles at the Isthmus of Panama. That is, the major axis of the Americas is north-south. The same is also true, though to a less extreme degree, for Africa. In contrast, the major axis of Eurasia is east-west. What effect, if any, did those differences on the orientation of the continent's axes have on human history? This chapter will be about what I see as their enormous, sometimes tragic consequences. Axis orientations affected the rate of spread of crops and livestock, and possibly also of writing, wheels, and other inventions. That basic feature of geography thereby contributed heavily to the very different experiences of Native Americans, Africans, and Eurasians in the last 500 years. Food production's spread proves as crucial to understanding geographic differences in the rise of guns, germs, and steel as did its origins, which we considered in the preceding chapters. That's because, as we saw, there were no more than 9 areas of the globe, perhaps as few as 5, where food production arose independently. Yet already in prehistoric times, food production became established in many other regions besides those few areas of origins. All those other areas became food-producing as a result of the spread of crops, livestock, and knowledge of how to grow them, and in some cases, as a result of migrations of farmers and herders themselves. The main such spreads of food production were from Southwest Asia to Europe, Egypt and North Africa, Ethiopia, Central Asia, and the Indus Valley, from the Sahel and West Africa to East and South Africa, from China to tropical Southeast Asia, the Philippines, Indonesia, Korea, and Japan, and from Mesoamerica to North America. Moreover, food production, even in its areas of origin, became enriched by the addition of crops, livestock, and techniques from other areas of origin. Just as some regions proved much more suitable than others for the origins of food production, the ease of its spread also varied greatly around the world. Some areas that are ecologically very suitable for food production never acquired it in prehistoric times at all, even though areas of prehistoric food production existed nearby. The most conspicuous such examples are the failure of both farming and herding to reach Native American California from the US Southwest, or to reach Australia from New Guinea and Indonesia, and the failure of farming to spread from South Africa's Natal province to South Africa's Cape. Even among all those areas where food production did spread in the prehistoric era, the rates and dates of spread varied considerably. At the one extreme was its rapid spread along east-west axes, from Southwest Asia both west to Europe and Egypt and east to the Indus Valley at an average rate of about 0.7 miles per year, and from the Philippines east to Polynesia at 3.2 miles per year. At the opposite extreme was its slow spread along north-south axes, at less than 0.5 miles per year from Mexico northward to the US Southwest, at less than 0.3 miles per year for corn and beans from Mexico northward to become productive in the eastern United States around AD 900, and at 0.2 miles per year for the llama from Peru north to Ecuador. These differences could be even greater if corn was not domesticated in Mexico as late as 3,500 BC, as I assumed conservatively for these calculations, and as some archaeologists now assume, but if it was instead domesticated considerably earlier, as most archaeologists used to assume, and many still do. There were also great differences in the completeness with which suites of crops and livestock spread, again implying stronger or weaker barriers to their spreading. For instance, while most of Southwest Asia's founder crops and livestock did spread west to Europe and east of the Indus Valley, Neither of the Andes' domestic mammals, the llama alpaca and the guinea pig, ever reached Mesoamerica in pre-Columbian times. That astonishing failure cries out for explanation. After all, Mesoamerica did develop dense farming populations and complex societies, so there can be no doubt that Andean domestic animals, if they had been available, would have been valuable for food, transport, and wool. Except for dogs, Mesoamerica was utterly without indigenous mammals to fill those needs. Some South American crops nevertheless did succeed in reaching Mesoamerica, such as manioc, sweet potatoes, and peanuts. What selective barrier let those crops through but screened out llamas and guinea pigs? A subtler expression of this geographically varying ease of spread is the phenomenon termed preemptive domestication. Most of the wild plant species from which our crops were derived vary genetically from area to area because alternative mutations had become established among the wild ancestral populations of different areas. Similarly, the changes required to transform wild plants into crops can in principle be brought about by alternative new mutations or alternative courses of selection to yield equivalent results. In this light, one can examine a crop widespread in prehistoric times and ask whether all of its varieties show the same wild mutation or same transforming mutation. The purpose of this examination is to try to figure out whether the crop was developed in just one area or else independently in several areas. If one carries out such a genetic analysis for major ancient New World crops, many of them prove to include two or more of those alternative wild variants, or two or more of those alternative transforming mutations. This suggests that the crop was domesticated independently in at least two different areas, and that some varieties of the crop inherited the particular mutation of one area, while other varieties of the same crop inherited the mutation of another area. On this basis, botanists conclude that lima beans, Phaseolus lunatus, common beans, Phaseolus vulgaris, and chili peppers of the Capsicum annuum chinense group were all domesticated on at least two separate occasions, once in Mesoamerica and once in South America, and that the squash Cucurbita pepo and the seed plant goosefoot were also domesticated independently at least twice, once in Mesoamerica and once in the eastern United States. In contrast, most ancient Southwest Asian crops exhibit just one of the alternative wild variants or alternative transforming mutations, suggesting that all modern varieties of that particular crop stem from only a single domestication. What does it imply if the same crop has been repeatedly and independently domesticated in several different parts of its wild range, and not just once and in a single area? We have already seen that plant domestication involves the modification of wild plants so that they become more useful to humans by virtue of larger seeds, a less bitter taste, or other qualities. Hence, if a productive crop is already available, incipient farmers will surely proceed to grow it rather than start all over again by gathering its not yet so useful wild relative and re-domesticating it. Evidence for just a single domestication thus suggests that once a wild plant had been domesticated, the crop spread quickly to other areas throughout the wild plant's range, preempting the need for other independent domestications of the same plant. However, when we find evidence that the same wild ancestor was domesticated independently in different areas, we infer that the crop spread too slowly to preempt its domestication elsewhere. The evidence for predominantly single domestications in Southwest Asia, but frequent multiple domestications in the Americas, might thus provide more subtle evidence that crops spread more easily out of Southwest Asia than in the Americas. Rapid spread of a crop may preempt domestication, not only of the same wild ancestral species somewhere else, but also of related wild species. If you're already growing good peas, it's of course pointless to start from scratch to domesticate the same wild ancestral pea again, but it's also pointless to domesticate closely related wild pea species, which for farmers are virtually equivalent to the already domesticated pea species. All of Southwest Asia's founder crops preempted domestication of any of their close relatives throughout the whole expanse of Western Eurasia. In contrast, the New World presents many cases of equivalent and closely related but nevertheless distinct species having been domesticated in Mesoamerica and South America. For instance, 95% of the cotton grown in the world today belongs to the cotton species Gossypium hirsutum, which was domesticated in prehistoric times in Mesoamerica. However, prehistoric South American farmers instead grew the related cotton Gossypium barbadens. Evidently, Mesoamerican cotton had such difficulty reaching South America that it failed in the prehistoric era to preempt the domestication of a different cotton species there, and vice versa. Chili peppers, squashes, amaranths, and canopods are other crops of which different but related species were domesticated in Mesoamerica and South America, since no species was able to spread fast enough to preempt the others. We thus have many different phenomena converging on the same conclusion, that food production spread more readily out of Southwest Asia than in the Americas, and possibly also than in sub-Saharan Africa. Those phenomena include food production's complete failure to reach some ecologically suitable areas, the differences in its rate and selectivity of spread, and the differences in whether the earliest domesticated crops preempted redomestications of the same species or domestications of close relatives. What was it about the Americas and Africa that made the spread of food production more difficult there than in Eurasia? To answer this question, let's begin by examining the rapid spread of food production out of Southwest Asia, the Fertile Crescent. Soon after food production arose there, somewhat before 8000 BC, a centrifugal wave of it appeared in other parts of Western Eurasia and North Africa, farther and farther removed from the Fertile Crescent to the west and east. I have redrawn a striking map assembled by the geneticist Daniel Zohari and botanist Maria Hopf, in which they illustrate how the wave had reached Greece and Cyprus and the Indian subcontinent by 6500 BC, Egypt soon after 6000 BC, Central Europe by 5400 BC, southern Spain by 5200 BC, and Britain around 3500 BC. In each of those areas, food production was initiated by some of the same suite of domestic plants and animals that launched it in the Fertile Crescent. In addition, the Fertile Crescent package penetrated Africa southward to Ethiopia at some still uncertain date. However, Ethiopia also developed many indigenous crops, and we do not yet know whether it was those crops or the arriving Fertile Crescent crops that launched Ethiopian food production. Of course, not all pieces of the package spread to all those outlying areas. For example, Egypt was too warm for einkorn wheat to become established. In some outlying areas, elements of the package arrived at different times. For instance, sheep preceded cereals in southwestern Europe. Some outlying areas went on to domesticate a few local crops of their own, such as poppies in western Europe and watermelons possibly in Egypt. But most food production in outlying areas depended initially on Fertile Crescent domesticates. Their spread was soon followed by that of other innovations originating in or near the Fertile Crescent, including the wheel, writing, metalworking techniques, milking, fruit trees, and beer and wine production. Why did the same plant package launch food production throughout Western Eurasia? Was it because the same set of plants occurred in the wild in many areas, were found useful there just as in the Fertile Crescent, and were independently domesticated? No, that's not the reason. First, many of the Fertile Crescent's founder crops don't even occur in the wild outside Southwest Asia. For instance, none of the 8 main founder crops except barley grows wild in Egypt. Egypt's Nile Valley provides an environment similar to the Fertile Crescent's Tigris and Euphrates valleys. Hence, the package that worked well in the latter valleys also worked well enough in the Nile Valley to trigger the spectacular rise of indigenous Egyptian civilization. But the foods to fuel that spectacular rise were originally absent in Egypt. The Sphinx and pyramids were built by people fed on crops originally native to the Fertile Crescent, not to Egypt. Second, even for those crops whose wild ancestor does occur outside of Southwest Asia, we can be confident that the crops of Europe and India were mostly obtained from Southwest Asia and were not local domesticates. For example, wild flax occurs west to Britain and Algeria and east to the Caspian Sea, while wild barley occurs east even to Tibet. However, for most of the Fertile Crescent's founding crops, all cultivated varieties in the world today share only one arrangement of chromosomes out of the multiple arrangements found in the wild ancestor. Or else they share only a single mutation, out of many possible mutations, by which the cultivated varieties differ from the wild ancestor in characteristics desirable to humans. For instance, all cultivated peas share the same recessive gene that prevents ripe pods of cultivated peas from spontaneously popping open and spilling their peas, as wild pea pods do. Evidently, most of the Fertile Crescent's founder crops were never domesticated again elsewhere after their initial domestication in the Fertile Crescent. Had they been repeatedly domesticated independently, they would exhibit legacies of those multiple origins in the form of varied chromosomal arrangements or varied mutations. Hence, these are typical examples of the phenomenon of preemptive domestication that we discussed above. The quick spread of the Fertile Crescent package preempted any possible other attempts, within the Fertile Crescent or elsewhere, to domesticate the same wild ancestors. Once the crop had become available, there was no further need to gather it from the wild and thereby set it on the path to domestication again. The ancestors of most of the founder crops have wild relatives, in the Fertile Crescent and elsewhere, that would also have been suitable for domestication. For example, peas belong to the genus Pisum, which consists of 2 wild species, Pisum sativum, the one that became domesticated to yield our garden peas, and Pisum fulvum, which was never domesticated. Yet wild peas of Pisum fulvum taste good, either fresh or dried, and are common in the wild. Similarly, wheats, barley, lentil, chickpea, beans, and flax all have numerous wild relatives besides the ones that became domesticated. Some of those related beans and barleys were indeed domesticated independently in the Americas or China, far from the early site of domestication in the Fertile Crescent. But in Western Eurasia, only one of several potentially useful wild species was domesticated, probably because that one spread so quickly that people soon stopped gathering the other wild relatives and ate only the crop. Again, as we discussed above, the crop's rapid spread preempted any possible further attempts to domesticate its relatives, as well as to redomesticate its ancestor.
What's up, Ruby?
Why was the spread of crops from the Fertile Crescent so rapid? The answer depends partly on that east-west axis of Eurasia with which I opened this chapter. Localities distributed east and west of each other at the same latitude share exactly the same day length and its seasonal variations. To a lesser degree, they also tend to share similar diseases, regimes of temperature and rainfall, and habitats or biomes, types of vegetation. For example, southern Italy, northern Iran, and Japan, all located at about the same latitude, but lying successively 4,000 miles east or west of each other, are more similar to each other in climate than each is to a location lying even a mere 1,000 miles due south. On all the continents, the habitat type known as tropical rainforest is confined to within about 10 degrees latitude of the equator, while Mediterranean scrub habitats, such as California's chaparral and Europe's maquis, lie between about 30 and 40 degrees of latitude. But the germination, growth, and disease resistance of plants are adapted to precisely those features of climate. Seasonal changes of day length, temperature, and rainfall constitute signals that stimulate seeds to germinate, seedlings to grow, and mature plants to develop flowers, seeds, and fruit. Each plant population becomes genetically programmed, through natural selection, to respond appropriately to signals of the seasonal regime under which it has evolved. Those regimes vary greatly with latitude. For example, day length is constant throughout the year at the equator, but at temperate latitudes it increases as the months advance from the winter solstice to the summer solstice, and it then declines again through the next half of the year. The growing season, that is the months with temperatures and day lengths suitable for plant growth, is shortest at high latitudes and longest toward the equator. Plants are also adapted to the diseases prevalent at their latitude. Woe betide the plant whose genetic program is mismatched to the latitude of the field in which it is planted. Imagine a Canadian farmer foolish enough to plant a race of corn adapted to growing farther south, in Mexico. The unfortunate corn plant, following its Mexico-adapted genetic program, would prepare to thrust up its shoots in March, only to find itself still buried under 10 feet of snow. Should the plant become genetically reprogrammed so as to germinate at a time more appropriate to Canada, say late June, the plant would still be in trouble for other reasons. Its genes would be telling it to grow at a leisurely rate sufficient only to bring it to maturity in 5 months. That's a perfectly safe strategy in Mexico's mild climate, but in Canada, a disastrous one that would guarantee the plants being killed by autumn frosts before it had produced any mature corn cobs. The plant would also lack genes for resistance to diseases of northern climates, while uselessly carrying genes for resistance to diseases of southern climates. All those features make low-latitude plants poorly adapted to high-latitude conditions and vice versa. As a consequence, most Fertile Crescent crops grow well in France and Japan, but poorly at the equator. Animals, too, are adapted to latitude-related features of climate. In that respect, we are typical animals, as we know by introspection. Some of us can't stand cold northern winters with their short days and characteristic germs, while others of us can't stand hot tropical climates with their own characteristic diseases. In recent centuries, overseas colonists from cool northern Europe have preferred to emigrate to the similarly cool climates of North America, Australia, and South Africa, and to settle in the cool highlands within equatorial Kenya and New Guinea. Northern Europeans who were sent out to hot tropical lowland areas used to die in droves of diseases such as malaria,
I
to which
improved
tropical
my
peoples
game.
had evolved some genetic resistance.
It's going a little bit
That's
better.
part of the reason why Fertile Crescent domesticates spread west and east so rapidly. They were already well adapted to the climates of the regions to which they were spreading. For instance, once farming crossed from the plains of Hungary into Central Europe around 5400 BC, it spread so quickly that the sites of the first farmers in the vast area from Poland west to Holland, marked by their characteristic pottery with linear decorations, were nearly contemporaneous. By the time of Christ, cereals of Fertile Crescent origin were growing over the 10,000-mile expanse from the Atlantic coast of Ireland to the Pacific coast of Japan. That west-east expansion of Eurasia is the largest land distance on Earth. Thus, Eurasia's west-east axis allowed Fertile Crescent crops quickly to launch agriculture over the band of temperate latitudes from Ireland to the Indus Valley, and to enrich the agriculture that arose independently in eastern Asia. Conversely, Eurasian crops that were first domesticated far from the Fertile Crescent but at the same latitudes were able to diffuse back to the Fertile Crescent. Today, when seeds are transported over the whole globe by ship and plane, we take it for granted that our meals are a geographic mishmash. A typical American fast food restaurant meal would include chicken, first domesticated in China, and potatoes from the Andes, or corn from Mexico, seasoned with black pepper from India, and washed down with a cup of coffee of Ethiopian origin. Already, though, by 2,000 years ago, Romans were also nourishing themselves with their own hodgepodge of foods that mostly originated elsewhere. Of Roman crops, only oats and poppies were native to Italy. Roman staples were the Fertile Crescent founder package, supplemented by quince, originating in the Caucasus, millet and cumin, domesticated in Central Asia, cucumber, sesame and citrus fruit from India, and chicken, rice, apricots, peaches, and foxtail millet, originally from China. Even though Rome's apples were at least native to Western Eurasia, they were grown by means of grafting techniques that had developed in China and spread westward from there. While Eurasia provides the world's widest band of land at the same latitude, and hence the most dramatic example of rapid spread of domesticates, there are other examples as well. Rivaling in speed the spread of the Fertile Crescent package was the eastward spread of a subtropical package that was initially assembled in South China, and that received additions on reaching tropical Southeast Asia, the Philippines, Indonesia, and New Guinea. Within 1,600 years, that resulting package of crops, including bananas, taro, and yams, and domestic animals, chickens, pigs, and dogs, had spread more than 5,000 miles eastward into the tropical Pacific to reach the islands of Polynesia. A further likely example is the east-west spread of crops within Africa's wide Sahel zone, but paleobotanists have yet to work out the details. Contrast the ease of east-west diffusion in Eurasia with the difficulties of diffusion along Africa's north-south axis. Most of the Fertile Crescent founder crops reached Egypt very quickly and then spread as far south as the cool highlands of Ethiopia, beyond which they didn't spread. South Africa's Mediterranean climate would have been ideal for them, but the 2,000 miles of tropical conditions between Ethiopia and South Africa posed an insuperable barrier. Instead, African agriculture south of the Sahara was launched by the domestication of wild plants, such as sorghum and African yams, indigenous to the Sahel zone and to tropical West Africa, and adapted to the warm temperatures, summer rains, and relatively constant day lengths of those low latitudes. Similarly, the spread southward of Fertile Crescent domestic animals through Africa was stopped or slowed by climate and disease, especially by trypanosome diseases carried by tsetse flies. The horse never became established farther south in West Africa's kingdoms north of the equator. The advance of cattle, sheep, and goats halted for 2,000 years at the northern edge of the Serengeti Plains, while new types of human economies and livestock breeds were being developed. Not until the period AD 1 to 200, some 8,000 years after livestock were domesticated in the Fertile Crescent, did cattle, sheep, and goats finally reach South Africa. Tropical African crops had their own difficulties spreading south in Africa, arriving in South Africa with black African farmers, the Bantu, just after those Fertile Crescent livestock did. However, those tropical African crops could never be transmitted across South Africa's Fish River, beyond which they were stopped by Mediterranean conditions to which they were not adapted. The result was the all-too-familiar course of the last 2 millennia of South African history. Some of South Africa's indigenous Khoisan peoples, otherwise known as Hottentots and Bushmen, acquired livestock but remained without agriculture. They became outnumbered and were replaced, northeast of the Fish River, by black African farmers, whose southward spread halted at that river. Only when European settlers arrived by sea in 1652, bringing with them their Fertile Crescent crop package, could agriculture thrive in South Africa's Mediterranean zone. The collisions of all those peoples produced the tragedies of modern South Africa, the quick decimation of the Khoisan by European germs and guns, a century of wars between Europeans and blacks, another century of racial oppression, and now efforts by Europeans and blacks to seek a new mode of coexistence in the former Khoisan lands. Contrast also the ease of diffusion in Eurasia with its difficulties along the Americas' north-south axis. The distance between Mesoamerica and South America, say between Mexico's highlands and Ecuador's, is only 1,200 miles, approximately the same as the distance in Eurasia separating the Balkans from Mesopotamia. The Balkans provided ideal growing conditions for most Mesopotamian crops and livestock, and received those domesticates as a package within 2,000 years of its assembly in the Fertile Crescent. That rapid spread preempted opportunities for domesticating those and related species in the Balkans. Highland Mexico and the Andes would similarly have been suitable for many of each other's crops and domestic animals. A few crops, notably Mexican corn, did indeed spread to the other region in the pre-Columbian era. But other crops and domestic animals failed to spread between Mesoamerica and South America. The cool highlands of Mexico would have provided ideal conditions for raising llamas, guinea pigs, and potatoes, all domesticated in the cool highlands of the South American Andes. Yet the northward spread of those Andean specialties was stopped completely by the hot, intervening lowlands of Central America. 5,000 years after llamas had been domesticated in the Andes, the Olmecs, Maya, Aztecs, and all other native societies of Mexico remained without pack animals and without any edible domestic mammals except for dogs. Conversely, domestic turkeys of Mexico and domestic sunflowers of the eastern United States might have thrived in the Andes, but their southward spread was stopped by the intervening tropical climates. The mere 700 miles of north-south distance prevented Mexican corn, squash, and beans from reaching the U.S. Southwest for several thousand years after their domestication in Mexico, and Mexican chili peppers and chenopods never did reach it in prehistoric times. For thousands of years after corn was domesticated in Mexico, it failed to spread northward into eastern North America because of the cooler climates and shorter growing season prevailing there. At some time between AD 1 and AD 200, corn finally appeared in the eastern United States, but only as a very minor crop. Not until around AD 900, after hardy varieties of corn adapted to northern climates had been developed, could corn-based agriculture contribute to the flowering of the most complex Native American society of North America, the Mississippian culture, a brief flowering ended by European-introduced germs arriving with and after Columbus. Recall that most Fertile Crescent crops prove, upon genetic study, to derive from only a single domestication process, whose resulting crop spread so quickly that it preempted any other incipient domestications of the same or related species. In contrast, many apparently widespread Native American crops prove to consist of related species or even of genetically distinct varieties of the same species, independently domesticated in Mesoamerica, South America, and the eastern United States. Closely related species replace each other geographically among the amaranths, beans, chenopods, chili peppers, cottons, squashes, and tobaccos. Different varieties of the same species replace each other among the kidney beans, lima beans, the chili pepper Capsicum annuum chinense, and the squash Cucurbita pepo. Those legacies of multiple independent domestications may provide further testimony to the slow diffusion of crops along the Americas' north-south axis. Africa and the Americas are thus the two largest land masses with a predominantly north-south axis and resultingly slow diffusion. In certain other parts of the world, slow north-south diffusion was important on a smaller scale. These other examples include the snail's pace of crop exchange between Pakistan's Indus Valley and South India, the slow spread of South Chinese food production into peninsular Malaysia, and the failure of tropical Indonesian and New Guinean food production to arrive in prehistoric times in the modern farmlands of southwestern and southeastern Australia, respectively. Those two corners of Australia are now the continent's breadbaskets, but they lie more than 2,000 miles south of the equator. Farming there had to await the arrival from faraway Europe, on European ships, of crops adapted to Europe's cool climate and short growing season. I have been dwelling on latitude, readily assessed by a glance at a map, because it is a major determinant of climate, growing conditions, and ease of spread of food production. However, latitude is of course not the only such determinant, and it is not always true that adjacent places at the same latitude have the same climate, though they do necessarily have the same day length. Topographic and ecological barriers, much more pronounced on some continents than on others, were locally important obstacles to diffusion. For instance, crop diffusion between the U.S. Southeast and Southwest was very slow and selective, although these two regions are at the same latitude. That's because much of the intervening area of Texas and the southern Great Plains was dry and unsuitable for agriculture. A corresponding example within Eurasia involved the eastern limit of Fertile Crescent crops, which spread rapidly westward to the Atlantic Ocean and eastward to the Indus Valley without encountering a major barrier. However, farther eastward in India, the shift from predominantly winter rainfall to predominantly summer rainfall contributed to a much more delayed extension of agriculture, involving different crops and farming techniques, into the Ganges plain of northeastern India. Still farther east, temperate areas of China were isolated from western Eurasian areas with similar climates by the combination of the Central Asian Desert, Tibetan Plateau, and Himalayas. The initial development of food production in China was therefore independent of that at the same latitude in the Fertile Crescent and gave rise to entirely different crops. However, even those barriers between China and Western Eurasia were at least partly overcome during the second millennium BC, when West Asian wheat, barley, and horses reached China. By the same token, the potency of a 2,000-mile north-south shift as a barrier also varies with local conditions. Fertile Crescent food production spread southward over that distance to Ethiopia, and Bantu food production spread quickly from Africa's Great Lakes region south to Natal, because in both cases, the intervening areas had similar rainfall regimes and were suitable for agriculture. In contrast, crop diffusion from Indonesia south to southwestern Australia was completely impossible, and diffusion over the much shorter distance from Mexico to the U.S. southwest and southeast was slow, because the intervening areas were deserts hostile to agriculture. The lack of a high-elevation plateau in Mesoamerica south of Guatemala, and Mesoamerica's extreme narrowness south of Mexico, and especially in Panama, were at least as important as the latitudinal gradient in throttling crop and livestock exchanges between the highlands of Mexico and the Andes. Continental differences in axis orientation affected the diffusion not only of food production, but also of other technologies and inventions. For example, around 3000 BC, the invention of the wheel in or near Southwest Asia spread rapidly west and east across much of Eurasia within a few centuries, whereas the wheels invented independently in prehistoric Mexico never spread south to the Andes. Similarly, the principle of alphabetic writing, developed in the western part of the Fertile Crescent by 1500 BC, spread west to Carthage and east to the Indian subcontinent within about 1,000 years. But the Mesoamerican writing systems that flourished in prehistoric times for at least 2,000 years never reached the Andes. Naturally, wheels and writing aren't directly linked to latitude and day length in the way crops are. Instead, the links are indirect, especially via food production systems and their consequences. The earliest wheels were parts of ox-drawn carts used to transport agricultural produce. Early writing was restricted to elites supported by food-producing peasants, and it served purposes of economically and socially complex food-producing societies, such as royal propaganda, goods inventories, and bureaucratic record-keeping. In general, societies that engaged in intense exchanges of crops, livestock, and technologies related to food production were more likely to become involved in other exchanges as well. America's patriotic song, America the Beautiful, invokes our spacious skies, our amber waves of grain, from sea to shining sea. Actually, that song reverses geographic realities. As in Africa, in the Americas, the spread of native crops and domestic animals was slowed by constricted skies and environmental barriers. No waves of native grain ever stretched from the Atlantic to the Pacific coast of North America, from Canada to Patagonia, or from Egypt to South Africa, while amber waves of wheat and barley came to stretch from the Atlantic to the Pacific across the spacious skies of Eurasia. That faster spread of Eurasian agriculture, compared with that of Native American and Sub-Saharan African agriculture, played a role, as the next part of this book will show, in the more rapid diffusion of Eurasian writing, metallurgy, technology, and empires. To bring up all those differences isn't to claim that widely distributed crops are admirable, or that they testify to the superior ingenuity of early Eurasian farmers. They reflect instead the orientation of Eurasia's axis, compared with that of the Americas or Africa. Around those axes turned the fortunes of history. Lethal gift of livestock, the evolution of germs. Some of us adults, even more of our children, pick up infectious diseases from our pets. Usually they remain no more than a nuisance, but a few have evolved into something far more serious. The major killers of humanity throughout our recent history, smallpox, flu, tuberculosis, malaria, plague, measles, and cholera, are infectious diseases that evolved from diseases of animals, even though most of the microbes responsible for our own epidemic illnesses are paradoxically now almost confined to humans. Because diseases have been the biggest killers of people, they have also been decisive shapers of history. Until World War II, more victims of war died of war-borne microbes than of battle wounds. All those military histories glorifying great generals oversimplify the ego-deflating truth. The winners of past wars were not always the armies with the best generals and weapons, but were often merely those bearing the nastiest germs to transmit to their enemies. The grimmest examples of germs' role in history come from the European conquest of the Americas that began with Columbus's voyage of 1492. Numerous as were the Native American victims of the murderous Spanish conquistadors, they were far outnumbered by the victims of murderous Spanish microbes. Why was the exchange of nasty germs between the Americas and Europe so unequal? Why didn't Native American diseases instead decimate the Spanish invaders, spread back to Europe, and wipe out 95% of Europe's population? Similar questions arise for the decimation of many other native peoples by Eurasian germs, as well as for the decimation of would-be European conquistadors in the tropics of Africa and Asia.
Yugi and Kaiba.
Thus, questions of the
Yugi-san. Yugi and Kaiba. The ultimate beyond. We use AI. AI to do this. Yeah, man, AI.
The animal origins of human disease lie behind the broadest pattern of human history and behind some of the most important issues in human health today. Think of AIDS, an explosively spreading human disease that appears to have evolved from a virus resident in wild African monkeys. Why did the rise of agriculture launch the evolution of our crowd infectious diseases? One reason is that agriculture sustains much higher human population densities than does the hunting-gathering lifestyle, on the average 10 to 100 times higher. In addition, hunter-gatherers frequently shift camp and leave behind their own piles of feces with accumulated microbes and worm larvae. But farmers are sedentary and live amid their own sewage, thus providing microbes with a short path from one person's body into another's drinking water. Some farming populations make it even easier for their own fecal bacteria and worms to infect new victims by gathering their feces and urine and spreading them as fertilizer in the fields where people work. Irrigation, agriculture, and fish farming provide ideal living conditions for the snails carrying shit.
Okay, we get something completely random, man. Draw 10. Nothing good. Draw 10. Nothing good.
Schistosomiasis, and for flukes that burrow through our skin as we wade through feces-laden water. Sedentary farmers become surrounded not only by their feces, but also by disease-transmitting rodents attracted by the farmers' stored food. The forest clearings made by African farmers also provide ideal breeding habitats for malaria-transmitting mosquitoes. If the rise of farming was thus a bonanza for our microbes, the rise of cities was a greater one, as still more densely packed human populations festered under even worse sanitation conditions. Not until the beginning of the 20th century did Europe's urban populations finally become self-sustaining. Before then, constant immigration of healthy peasants from the countryside was necessary to make up for the constant deaths of city dwellers from crowd diseases. Another bonanza was the development of world trade routes, which by Roman times effectively joined the populations of Europe, Asia, and North Africa into one giant breeding ground for microbes. That's when smallpox finally reached Rome as the plague of Antoninus, which killed millions of Roman citizens between AD 165 and 180. Similarly, bubonic plague first appeared in Europe as the plague of Justinian, AD 542 to 43. But plague didn't begin to hit Europe with full force as the Black Death epidemics until AD 1346, when a new route for overland trade with China provided rapid transit along Eurasia's east-west axis for flea-infested furs from plague-ridden areas of Central Asia to Europe. Today, our jet planes have made even the longest intercontinental flights briefer than the duration of any human infectious disease. That's how an Aerolíneas Argentinas airplane, stopping in Lima, Peru in 1991, managed to deliver dozens of cholera-infected people that same day to my city of Los Angeles, over 3,000 miles from Lima. The explosive increase in world travel by Americans and in immigration to the United States is turning us into another melting pot, this time of microbes that we previously dismissed as just causing exotic diseases in far-off countries. Thus, when the human population became sufficiently large and concentrated, we reached the stage in our history at which we could at last evolve and sustain crowd diseases confined to our own species. But that conclusion presents a paradox. Such diseases could never have existed before then. Instead, they had to evolve as new diseases. Where did those new diseases come from? Evidence has recently been emerging from molecular studies of the disease-causing microbes themselves. For many of the microbes responsible for our unique diseases, molecular biologists can now identify the microbes' closest relatives. These also prove to be agents of crowd infectious diseases, but ones confined to various species of our domestic animals and pets. Among animals, too, epidemic diseases require large, dense populations and don't afflict just any animal. They're confined mainly to social animals providing the necessary large population. Hence, when we domesticated social animals, such as cows and pigs, they were already afflicted by epidemic diseases just waiting to be transferred to us. For example, measles virus is most closely related to the virus causing rinderpest. That nasty epidemic disease affects cattle and many wild cud-chewing mammals, but not humans. Measles, in turn, don't afflict cattle. The close similarity of the measles virus to the rinderpest virus suggests that the latter transferred from cattle to humans and then evolved into the measles virus by changing its properties to adapt to us. That transfer is not at all surprising, considering that many peasant farmers live and sleep close to cows and their feces, urine, breath, sores, and blood. Our intimacy with cattle has been going on for the 9,000 years since we domesticated them, ample time for the rinderpest virus to discover us nearby. Others of our familiar infectious diseases can similarly be traced back to diseases of our animal friends. Given our proximity to the animals we love, we must be getting constantly bombarded by their microbes. Those invaders get winnowed by natural selection, and only a few of them succeed in establishing themselves as human diseases. A quick survey of current diseases lets us trace out 4 stages in the evolution of a specialized human disease from an animal precursor. The first stage is illustrated by dozens of diseases that we now and then pick up directly from our pets and domestic animals. They include cat scratch fever from our cats, leptospirosis from our dogs, psittacosis from our chickens and parrots, and brucellosis from our cattle. We're similarly liable to pick up diseases from wild animals, such as the tularemia that hunters can get from skinning wild rabbits. All those microbes are still at an early stage in their evolution into specialized human pathogens. They still don't get transmitted directly from one person to another, and even their transfer to us from animals remains uncommon. In the second stage, a former animal pathogen evolves to the point where it does get transmitted directly between people and causes epidemics. However, the epidemic dies out for any of several reasons, such as being cured by modern medicine or being stopped when everybody around has already been infected and either becomes immune or dies. For example, a previously unknown fever termed Onyongyong fever appeared in East Africa in 1959 and proceeded to infect several million Africans. It probably arose from a virus of monkeys and was transmitted to humans by mosquitoes. The fact that patients recovered quickly and became immune to further attack helped the new disease die out quickly. Closer to home for Americans, Fort Bragg fever was the name applied to a new leptospiral disease that broke out in the United States in the summer of 1942 and soon disappeared. A fatal disease vanishing for another reason was New Guinea's laughing sickness, transmitted by cannibalism and caused by a slow-acting virus from which no one has ever recovered. Kuru was on its way to exterminating New Guinea's foray tribe of 20,000 people until the establishment of Australian government control around 1959 ended cannibalism and thereby the transmission of Kuru. The annals of medicine are full of accounts of diseases that sound like no disease known today, but that once caused terrifying epidemics and then disappeared as mysteriously as they had come. The English sweating sickness, which swept and terrified Europe between 1485 and 1552, and the Picardy sweats of 18th and 19th century France, are just two of the many epidemic illnesses that vanished long before modern medicine had devised methods for identifying the responsible microbes. The third stage in the evolution of our major diseases is represented by former animal pathogens that did establish themselves in humans, that have not yet, died out, and that may or may not still become major killers of humanity. The future remains very uncertain for Lassa fever, caused by a virus derived probably from rodents. Lassa fever was first observed in 1969 in Nigeria, where it causes a fatal illness so contagious that Nigerian hospitals have been closed down if even a single case appears. Better established is Lyme disease, caused by a spirochete that we get from the bite of ticks carried by mice and deer. Although the first known human cases in the United States appeared only as recently as 1962, Lyme disease is already reaching epidemic proportions in many parts of our country. The future of AIDS, derived from monkey viruses and first documented in humans around 1959, is even more secure, from the virus's perspective. The final stage of this evolution is represented by the major long-established epidemic diseases confined to humans. These diseases must have been the evolutionary survivors of far more pathogens that tried to make the jump to us from animals, and mostly failed. What is actually going on in those stages as an exclusive disease of animals transforms itself into an exclusive disease of humans? One transformation involves a change of intermediate vector. When a microbe relying on some arthropod vector for transmission switches to a new host, the microbe may be forced to find a new arthropod as well. For example, typhus was initially transmitted between rats by rat fleas, which sufficed for a while to transfer typhus from rats to humans. Eventually, typhus microbes discovered that human body lice offered a much more efficient method of traveling directly between humans. Now that Americans have mostly deloused themselves, typhus has discovered a new route into us, by infecting eastern North American flying squirrels and then transferring to people whose attics harbor flying squirrels. In short, diseases represent evolution in progress, and microbes adapt by natural selection to new hosts and vectors. But compared with cows' bodies, ours offer different immune defenses, lice, feces, and chemistries. In that new environment, a microbe must evolve new ways to live and to propagate itself. In several instructive cases, doctors or veterinarians have actually been able to observe microbes evolving those new ways. The best studied case involves what happened when myxomatosis hit Australian rabbits. The myxovirus, native to a wild species of Brazilian rabbit, had been observed to cause a lethal epidemic in European domestic rabbits, which are a different species. Hence, the virus was intentionally introduced to Australia in 1950 in the hopes of ridding the continent of its plague of European rabbits, foolishly introduced in the 19th century. In the first year, myxo produced a gratifying, to Australian farmers, 99.8% mortality rate in infected rabbits. Unfortunately for the farmers, the death rate then dropped in the second year to 90% and eventually to 25%, frustrating hopes of eradicating rabbits completely from Australia. The problem was that the myxovirus evolved to serve its own interests, which differed from ours as well as from those of the rabbits. The virus changed so as to kill fewer rabbits and to permit lethally infected ones to live longer before dying. As a result, a less lethal myxovirus spreads baby viruses to more rabbits than did the original, highly virulent myxo. For a similar example in humans, we have only to consider the surprising evolution of syphilis. Today, our two immediate associations to syphilis are genital sores and a very slowly developing disease leading to the death of many untreated victims only after many years. However, when syphilis was first definitely recorded in Europe in 1495, its pustules often covered the body from the head to the knees, caused flesh to fall off people's faces, and led to death within a few months. By 1546, syphilis had evolved into the disease with the symptoms so well known to us today. Apparently, just as with myxomatosis, those syphilis spirochetes that evolved so as to keep their victims alive for longer were thereby able to transmit their spirochete offspring into more victims. The importance of lethal microbes in human history is well illustrated by Europeans' conquest and depopulation of the New World. Far more Native Americans died in bed from Eurasian germs than on the battlefield from European guns and swords. Those germs undermined Indian resistance by killing most Indians and their leaders and by sapping the survivors' morale. For instance, in 1519, Cortés landed on the coast of Mexico with 600 Spaniards, who conquered the fiercely militaristic Aztec Empire with a population of many millions. Cortés reached the Aztec capital of Tenochtitlan, escaped with the loss of only two-thirds of his force, and managed to fight his way back to the coast, demonstrates both Spanish military advantages and the initial naivete of the Aztecs. But when Cortés' next onslaught came, the Aztecs were no longer naive and fought street by street with the utmost tenacity. What gave the Spaniards a decisive advantage was smallpox, which reached Mexico in 1520 with one infected slave arriving from Spanish Cuba. The resulting epidemic proceeded to kill nearly half of the Aztecs, including Emperor Cuitlahuac. Aztec survivors were demoralized by the mysterious illness that killed Indians and spared Spaniards, as if advertising the Spaniards' invincibility. By 1618, Mexico's initial population of about 20 million had plummeted to about 1.6 million. Pizarro had similarly grim luck when he landed on the coast of Peru in 1531 with 168 men to conquer the Inca Empire of millions. Fortunately for Pizarro, and unfortunately for the Incas, smallpox had arrived overland around 1526, killing much of the Inca population, including both the Emperor Huayna Capac and his designated successor. The result of the thrones being left vacant was that two other sons of Huayna Capac, Atahualpa and Huascar, became embroiled in a civil war that Pizarro exploited to conquer the divided Incas. When we in the United States think of the most populous New World societies existing in 1492, only those of the Aztecs and the Incas tend to come to our minds. We forget that North America also supported populous Indian societies in the most logical place, the Mississippi Valley, which contains some of our best farmland today. In that case, however, conquistadors contributed nothing directly to the society's destruction. Eurasian germs, spreading in advance, did everything. When Hernando de Soto became the first European conquistador to march through the southeastern United States in 1540, he came across Indian towns spreading. By the time of the next appearance of Europeans on the lower Mississippi, that of French settlers in the late 1600s, almost all of those big Indian towns had vanished. Their relics are great mound sites of the Mississippi Valley. Only recently have we come to realize that many of the mound-building societies were still largely intact when Columbus reached the New World, and that they collapsed, probably as a result of disease, between 1492 and the systematic European exploration of the Mississippi. When I was young, American schoolchildren were taught that North America had originally been occupied by only about 1 million Indians. That low number was useful in justifying the white conquest of what could be viewed as an almost empty continent. However, archaeological excavations and scrutiny of descriptions left by the very first European explorers on our coasts now suggest an initial number of around 20 million Indians. For the New World as a whole, the Indian population decline in the century or two following Columbus's arrival is estimated to have been as large as 95%. The main killers were Old World germs, to which Indians had never been exposed, and against which they therefore had neither immune nor genetic resistance. Smallpox, measles, influenza, and typhus competed for top rank among the killers. As if these had not been enough, diphtheria, malaria, mumps, pertussis, plague, tuberculosis, and yellow fever came up close behind. In countless cases, whites were actually there to witness the destruction occurring when the germs arrived. For example, in 1837, the Mandan Indian tribe, with one of the most elaborate cultures in our Great Plains, contracted smallpox from a steamboat traveling up the Missouri River from St. Louis. The population of one Mandan village plummeted from 2,000 to fewer than 40 within a few weeks. While over a dozen major infectious diseases of Old World origins became established in the New World, perhaps not a single major killer reached Europe from the Americas. The sole possible exception is syphilis, whose area of origin remains controversial. The one-sidedness of that exchange of germs becomes even more striking when we recall that large, dense human populations are a prerequisite for the evolution of our crowd infectious diseases. If recent reappraisals of the pre-Columbian New World population are correct, it was not far below the contemporary population of Eurasia. Some New World cities like Tenochtitlan were among the world's most populous cities at the time. Why didn't Tenochtitlan have awful germs waiting for the Spaniards? One possible contributing factor is that the rise of dense human populations began somewhat later in the New World than in the Old World. Another is that the three most densely populated American centers, the Andes, Mesoamerica, and the Mississippi Valley, never became connected by regular fast trade into one huge breeding ground for microbes in the way that Europe, North Africa, India, and China became linked in Roman times. Those factors still don't explain, though, why the New World apparently ended up with no lethal crowd epidemics at all. Tuberculosis DNA has been reported from the mummy of a Peruvian Indian who died 1,000 years ago, but the identification procedure used did not distinguish human tuberculosis from a closely related pathogen, Mycobacterium bovis, that is widespread in wild animals. Instead, what must be the main reason for the failure of lethal crowd epidemics to arise in the Americas becomes clear when we pause to ask a simple question. From what microbes could they conceivably have evolved? We've seen that Eurasian crowd diseases evolved out of diseases of Eurasian herd animals that became domesticated. Whereas many such animals existed in Eurasia, only 5 animals of any sort became domesticated in the Americas. The turkey in Mexico and the U.S. Southwest, the llama alpaca and the guinea pig in the Andes, the Muscovy duck in tropical South America, and the dog throughout the Americas. In turn, we also saw that this extreme paucity of domestic animals in the New World reflects the paucity of wild starting material. About 80% of the big wild mammals of the Americas became extinct at the end of the last ice age, around 13,000 years ago. The few domesticates that remained to Native Americans were not likely sources of crowd diseases compared with cows and pigs. Muscovy ducks and turkeys don't live in enormous flocks, and they're not cuddly species, like young lambs, with which we have much physical contact. Guinea pigs may have contributed a trypanosome infection like Chagas' disease or leishmaniasis to our catalogue of woes, but that's uncertain. Initially, most surprising is the absence of any human disease derived from llamas or alpacas, which it's tempting to consider the Andean equivalent of Eurasian livestock. However, llamas had 4 strikes against them as a sort of human pathogens. They were kept in smaller herds than were sheep and goats and pigs. Their total numbers were never remotely as large as those of the Eurasian populations of domestic livestock, since llamas never spread beyond the Andes. People don't drink and get infected by llama milk, and llamas aren't kept indoors in close association with people. In contrast, human mothers in the New Guinea highlands often nurse piglets, and pigs as well as cows are frequently kept inside the huts of peasant farmers. The historical importance of animal-derived diseases extends far beyond the collision of the Old and the New Worlds. Eurasian germs played a key role in decimating native peoples in many other parts of the world, including Pacific Islanders, Aboriginal Australians, and the Khoisan peoples, Hottentots and Bushmen, of southern Africa. Cumulative mortalities of these previously unexposed peoples from Eurasian germs ranged from 50% to 100%. For instance, the Indian population of Hispaniola declined from around 8 million when Columbus arrived in AD 1492 to 0 by 1535. Measles reached Fiji with a Fijian chief returning from a visit to Australia in 1875 and proceeded to kill about 1/4 of all Fijians then alive, after most Fijians had already been killed by epidemics beginning with the first European visit in 1791. Syphilis, gonorrhea, tuberculosis, and influenza, arriving with Captain Cook in 1779, followed by a big typhoid epidemic in 1804 and numerous minor epidemics, reduced Hawaii's population from around 500,000 in 1779 to 84,000 in 1853, the year when smallpox finally reached Hawaii and killed around 10,000 of the survivors. These examples could be multiplied almost indefinitely. However, germs did not act solely to Europeans' advantage. While the New World and Australia did not harbor native epidemic diseases awaiting Europeans, tropical Asia, Africa, Indonesia, and New Guinea certainly did. Malaria throughout the tropical Old World, cholera in tropical Southeast Asia, and yellow fever in tropical Africa were, and still are, the most notorious of the tropical killers. They posed the most serious obstacle to European colonization of the tropics, and they explain why the European colonial partitioning of New Guinea and most of Africa was not accomplished until nearly 400 years after the European partitioning of the New World began. Furthermore, once malaria and yellow fever did become transmitted to the Americas by European ship traffic, they emerged as the major impediment to the colonization of the New World tropics as well. A familiar example is the role of these two diseases in aborting the French effort and nearly aborting the ultimately successful American effort to construct the Panama Canal. Bearing all these facts in mind, let's try to regain our sense of perspective about the role of germs in answering Yali's question. There is no doubt that Europeans developed a big advantage in weaponry, technology, and political organization over most of the non-European peoples that they conquered. But that advantage alone doesn't fully explain how initially so few European immigrants came to supplant so much of the native population of the Americas and some other parts of the world. That might not have happened without Europe's sinister gift to other continents, the germs evolving from Eurasians' long intimacy with domestic animals. Blueprints and borrowed letters, the evolution of writing. 19th century authors tended to interpret history as a progression from savagery to civilization. Key hallmarks of this transition included the development of agriculture, metallurgy, complex technology, centralized government, and writing. Of these, writing was traditionally the one most restricted geographically. Until the expansions of Islam and of colonial Europeans, it was absent from Australia, Pacific Islands, sub-equatorial Africa, and the whole New World except for a small part of Mesoamerica. As a result of that confined distribution, peoples who pride themselves on being civilized have always viewed writing as the sharpest distinction raising them above barbarians or savages. Knowledge brings power. Hence, writing brings power to modern societies by making it possible to transmit knowledge with far greater accuracy and in far greater quantity and detail from more distant lands and more remote times. Of course, some peoples, notably the Incas, managed to administer empires without writing, and civilized peoples don't always defeat barbarians, as Roman armies facing the Huns learned. But the European conquests of the Americas, Siberia, and Australia illustrate the typical recent outcome. Writing marched together with weapons, microbes, and centralized political organization as a modern agent of conquest. The commands of the monarchs and merchants who organized colonizing fleets were conveyed in writing. The fleets set their courses by maps and written sailing directions prepared by previous expeditions. Written accounts of earlier expeditions motivated later ones by describing the wealth and fertile lands awaiting the conquerors. The accounts taught subsequent explorers what conditions to expect and helped them prepare themselves. The resulting empires were administered with the aid of writing. While all those types of information were also transmitted by other means in pre-literate societies, writing made the transmission easier, more detailed, more accurate, and more persuasive. Why then did only some peoples and not others develop writing, given its overwhelming value? For example, why did no traditional hunters-gatherers evolve or adopt writing? Among island empires, why did writing arise in Minoan Crete, but not in Polynesian Tonga? How many separate times did writing evolve in human history, under what circumstances, and for what uses? Of those peoples who did develop it, why did some do so much earlier than others? For instance, today almost all Japanese and Scandinavians are literate, but most Iraqis are not. Why did writing nevertheless arise nearly 4,000 years earlier in Iraq? The diffusion of writing from its sites of origin also raises important questions. Why, for instance, did it spread to Ethiopia and Arabia from the Fertile Crescent, but not to the Andes from Mexico? Did writing systems spread by being copied, or did existing systems merely inspire neighboring peoples to invent their own systems? Given a writing system that works well for one language, how do you devise a system for a different language? Similar questions arise whenever one tries to understand the origins and spread of many other aspects of human culture, such as technology, religion, and food production. The historian interested in such questions about writing has the advantage that they can often be answered in unique detail by means of the written record itself. We shall therefore trace writing's development not only because of its inherent importance, but also for the general insights into cultural history that it provides. With the possible exceptions of the Egyptian, Chinese, and Easter Island writing to be considered later, all other writing systems, devised anywhere in the world at any time, appear to have been descendants of systems modified from, or at least inspired by, Sumerian or early Mesoamerican writing. One reason why there were so few independent origins of writing is the great difficulty of inventing it. The other reason is that other opportunities for the independent invention of writing were preempted by Sumerian or early Mesoamerican writing and their derivatives. We know that the development of Sumerian writing took at least hundreds, possibly thousands of years. As we shall see, the prerequisites for those developments consisted of several features of human society that determined whether a society would find writing useful and whether the society could support the necessary specialist scribes. Many other human societies besides those of the Sumerians and early Mexicans, such as those of ancient India, Crete, and Ethiopia, evolved these prerequisites. However, the Sumerians and early Mexicans happen to have been the first to evolve them in the Old World and the New World, respectively. Once the Sumerians and early Mexicans had invented writing, the details or principles of their writing spread rapidly to other societies before they could go through the necessary centuries or millennia of independent experimentation with writing themselves. Thus, that potential for other independent experiments was preempted or aborted. The spread of writing has occurred by either of two contrasting methods, which find parallels throughout the history of technology and ideas. Someone invents something and puts it to use. How do you, another would-be user, then design something similar for your own use, knowing that other people have already got their own model built and working? Such transmission of inventions assumes a whole spectrum of forms. At the one end lies blueprint copying, when you copy or modify an available detailed blueprint. At the opposite end lies idea diffusion, when you receive little more than the basic idea and have to reinvent the details. Knowing that it can be done stimulates you to try to do it yourself, but your eventual specific solution may or may not resemble that of the first inventor. To take a recent example, historians are still debating whether blueprint copying or idea diffusion contributed more to Russia's building of an atomic bomb. Did Russia's bomb-building efforts depend critically on blueprints of the already constructed American bomb stolen and transmitted to Russia by spies? Or was it merely that the revelation of America's A-bomb at Hiroshima at last convinced Stalin of the feasibility of building such a bomb, and that Russian scientists then reinvented the principles in an independent crash program with little detailed guidance from earlier American effort? Similar questions arise for the history of the development of wheels, pyramids, and gunpowder. Let us now return to the main question with which we began this chapter. Why did writing arise in and spread to some societies, but not to many others? Convenient starting points for our discussion are the limited capabilities, uses, and users of early writing systems. Early scripts were incomplete, ambiguous, or complex, or all three. For example, the oldest Sumerian cuneiform writing could not render normal prose, but was a mere telegraphic shorthand, whose vocabulary was restricted to names, numerals, units of measure, words for objects counted, and a few adjectives. That's as if a modern American court clerk were forced to write John 27 fat sheep, because English writing lacked the necessary words and grammar to write, "We order John to deliver the 27 fat sheep that he owes to the government." Later Sumerian cuneiform did become capable of rendering prose, but it did so by a messy system with mixtures of logograms, phonetic signs, and unpronounced determinatives totaling hundreds of separate signs. Linear B, the writing of Mycenaean Greece, was at least simpler, being based on a syllabary of about 90 signs plus logograms. Offsetting that virtue, Linear B was quite ambiguous. It omitted any consonant at the end of a word, and it used the same sign for several related consonants. For instance, one sign for both L and R, another for P and B and PH, and still another for G and K and KH. We know how confusing we find it when native-born Japanese people speak English without distinguishing L and R. Imagine the confusion if our alphabet did the same, while similarly homogenizing the other consonants that I mentioned. It's as if we were to spell the words rap, lap, lab, and laugh identically. A related limitation is that few people ever learned to write these early scripts. Knowledge of writing was confined to professional scribes in the employ of the king or temple. For instance, there was no hint that Linear B was used or understood by any Mycenaean Greek beyond small cadres of palace bureaucrats. Since individual Linear B scribes can be distinguished by their handwriting on preserved documents, we can say that all preserved Linear B documents from the palaces of Knossos and Pylos are the work of a mere 75 and 40 scribes, respectively. The uses of these telegraphic, clumsy, ambiguous early scripts were as restricted as the number of their users. Anyone hoping to discover how Sumerians of 3000 BC thought and felt is in for a disappointment. Instead, the first Sumerian texts are emotionless accounts of palace and temple bureaucrats. About 90% of the tablets in the earliest known Sumerian archives, from the city of Uruk, are clerical records of goods paid in, workers given rations, and agricultural products distributed. Only later, as Sumerians progressed beyond logograms to phonetic writing, did they begin to write prose narratives, such as propaganda and myths. Mycenaean Greeks never even reached that propaganda and myths stage. 1/3 of all Linear B tablets from the Palace of Knossos are accountants' records of sheep and wool, while an inordinate proportion of writing at the Palace of Pylos consists of records of flax. Linear B was inherently so ambiguous that it remained restricted to palace accounts, whose context and limited word choices made the interpretation clear. Not a trace of its use for literature has survived. The Iliad and Odyssey were composed and transmitted by non-literate bards for non-literate listeners, and not committed to writing until the development of the Greek alphabet hundreds of years later. Similarly restricted uses characterize early Egyptian, Mesoamerican, and Chinese writing. Early Egyptian hieroglyphs recorded religious and state propaganda and bureaucratic accounts. Preserved Maya writing was similarly devoted to propaganda, births and accessions and victories of kings, and astronomical observations of priests. The oldest preserved Chinese writing of the late Shang dynasty consists of religious divination about dynastic affairs, incised into so-called oracle bones. A sample Shang text: "The king, reading the meaning of the crack, in a bone cracked by heating, said, 'If the child is born on a Kang day, it will be extremely auspicious.'" To us today, it is tempting to ask why societies with early writing systems accepted the ambiguities that restricted writing to a few functions and a few scribes. But even to pose that question is to illustrate the gap between ancient perspectives and our own expectations of mass literacy. The intended restricted uses of early writing provided a positive disincentive for devising less ambiguous writing systems. The kings and priests of ancient Sumer wanted writing to be used by professional scribes to record numbers of sheep owed in taxes, not by the masses to write poetry and hatch plots. As the anthropologist Claude Lévi-Strauss put it, ancient writing's main function was to facilitate the enslavement of other human beings. Personal uses of writing by non-professionals came only much later, as writing systems grew simpler and more expressive. For instance, with the fall of Mycenaean Greek civilization around 1200 BC, linear B disappeared, and Greece returned to an age of pre-literacy. When writing finally returned to Greece in the 8th century BC, the new Greek writing, its users and its uses were very different. The writing was no longer an ambiguous syllabary mixed with logograms, but an alphabet borrowed from the Phoenician consonantal alphabet and improved by the Greek invention of vowels. In place of lists of sheep, legible only to scribes and read only in palaces, Greek alphabetic writing from the moment of its appearance was a vehicle of poetry and humor, to be read in private homes. For instance, the first preserved example of Greek alphabetic writing, scratched onto an Athenian wine jug of about 740 BC, is a line of poetry announcing a dancing contest. Whoever of all dancers performs most nimbly will win this vase as a prize. The next example is 3 lines of dactylic hexameter scratched onto a drinking cup. I am Nestor's delicious drinking cup. Whoever drinks from this cup swiftly will the desire of fair-crowned Aphrodite seize him. The earliest preserved examples of the Etruscan and Roman alphabets are also inscriptions on drinking cups and wine containers. Only later did the alphabet's easily learned vehicle of private communication become co-opted for public or bureaucratic purposes. Thus, the developmental sequence of uses for alphabetic writing was the reverse of that for the earlier systems of logograms and syllabaries. The limited uses and users of early writing suggest why writing appeared so late in human evolution. All of the likely or possible independent inventions of writing in Sumer, Mexico, China, and Egypt, and all of the early adaptations of those invented systems, for example, those in Crete, Iran, Turkey, the Indus Valley, and the Maya area, involved socially stratified societies with complex and centralized political institutions, whose necessary relation to food production we shall explore in a later chapter. Early writing served the needs of those political institutions, such as record-keeping and royal propaganda, and the users were full-time bureaucrats nourished by stored food surpluses grown by food-producing peasants. Writing was never developed or even adopted by hunter-gatherer societies because they lacked both the institutional uses of early writing and the social and agricultural mechanisms for generating the food surpluses required to feed scribes. Thus, food production and thousands of years of societal evolution following its adoption were as essential for the evolution of writing as for the evolution of microbes causing human epidemic diseases. Writing arose independently only in the Fertile Crescent, Mexico, and probably China, precisely because those were the first areas where food production emerged in their respective hemispheres. Once writing had been invented by those few societies, it then spread, by trade and conquest and religion, to other societies with similar economies and political organizations. While food production was thus a necessary condition for the evolution or early adoption of writing, it was not a sufficient condition. At the beginning of this chapter, I mentioned the failure of some food-producing societies with complex political organization to develop or adopt writing before modern times. Those cases, initially so puzzling to us moderns accustomed to viewing writing as indispensable to a complex society, included one of the world's largest empires as of AD 1520, the Inca Empire of South America. They also included Tonga's maritime proto-empire, the Hawaiian state emerging in the late 18th century, all of the states and chiefdoms of sub-equatorial Africa and sub-Saharan West Africa before the arrival of Islam, and the largest native North American societies, those of the Mississippi Valley and its tributaries. Why did all those societies fail to acquire writing, despite their sharing prerequisites with societies that did do so? Here we have to remind ourselves that the vast majority of societies with writing acquired it by borrowing it from neighbors or by being inspired by them to develop it, rather than by independently inventing it themselves. The societies without writing that I just mentioned are ones that got a later start on food production than did Sumer, Mexico, and China. The only uncertainty in this statement concerns the relative dates for the onset of food production in Mexico and in the Andes, the eventual Inca realm. Given enough time, the societies lacking writing might also have eventually developed it on their own. Had they been located nearer to Sumer, Mexico, and China, they might instead have acquired writing or the idea of writing from those centers, just as did India, the Maya, and most other societies with writing. But they were too far from the first centers of writing to have acquired it before modern times. The importance of isolation is most obvious for Hawaii and Tonga, both of which were separated by at least 4,000 miles of ocean from the nearest societies with writing. The other societies illustrate the important point that distance as the crow flies is not an appropriate measure of isolation for humans. The Andes, West Africa's kingdoms, and the mouth of the Mississippi River lay only about 1,200, 1,500, and 700 miles, respectively, from societies with writing in Mexico, North Africa, and Mexico, respectively. These distances are considerably less than the distances the alphabet had to travel from its homeland on the eastern shores of the Mediterranean to reach Ireland, Ethiopia, and Southeast Asia within 2,000 years of its invention. But humans are slowed by ecological and water barriers that crows can fly over. The states of North Africa, with writing, and West Africa, without writing, were separated from each other by Saharan desert, unsuitable for agriculture and cities. The deserts of northern Mexico similarly separated the urban centers of southern Mexico from the chiefdoms of the Mississippi Valley. Communication between southern Mexico and the Andes required either a sea voyage or else a long chain of overland contacts via the narrow, forested, never urbanized Isthmus of Darien. Hence, the Andes, West Africa, and the Mississippi Valley were effectively rather isolated from societies with writing. That's not to say that those societies without writing were totally isolated. West Africa eventually did receive Fertile Crescent domestic animals across the Sahara, and later accepted Islamic influence, including Arabic writing. Corn diffused from Mexico to the Andes and, more slowly, from Mexico to the Mississippi Valley. But we already saw that the north-south axes and ecological barriers within Africa and the Americas retarded the diffusion of crops and domestic animals. The history of writing illustrates strikingly the similar ways in which geography and ecology influenced the spread of human inventions. Necessity's mother, the evolution of technology. Technology, in the form of weapons and transport, provides the direct means by which certain peoples have expanded their realms and conquered other peoples. That makes it the leading cause of history's broadest pattern. But why were Eurasians, rather than Native Americans or Sub-Saharan Africans, the ones to invent firearms, ocean-going ships, and steel equipment? The differences extend to most other significant technological advances, from printing presses to glass and steam engines. Why were all those inventions Eurasian? Why were all New Guineans and Native Australians in AD 1800 still using stone tools like ones discarded thousands of years ago in Eurasia and most of Africa, even though some of the world's richest copper and iron deposits are in New Guinea and Australia, respectively? All those facts explain why so many lay people assume that Eurasians are superior to other peoples in inventiveness and intelligence. If, on the other hand, no such difference in human neurobiology exists to account for continental differences in technological development, what does account for them? An alternative view rests on the heroic theory of invention. Technological advances seem to come disproportionately from a few very rare geniuses, such as Johannes Gutenberg, James Watt, Thomas Edison, and the Wright brothers. They were Europeans or descendants of European emigrants to America. So were Archimedes and other rare geniuses of ancient times. Could such geniuses have equally well been born in Tasmania or Namibia? Does the history of technology depend on nothing more than accidents of the birthplaces of a few inventors? Still another alternative view holds that it is a matter not of individual inventiveness, but of the receptivity of whole societies to innovation. Some societies seem hopelessly conservative, inward-looking, and hostile to change. That's the impression of many Westerners who have attempted to help third-world peoples and ended up discouraged. The people seem perfectly intelligent as individuals. The problem seems instead to lie with their societies. How else can one explain why the Aborigines of northeastern Australia failed to adopt bows and arrows, which they saw being used by Torres Straits Islanders with whom they traded? Might all the societies of an entire continent be unreceptive, thereby explaining technology's slow pace of development there? In this chapter, we shall finally come to grips with the central problem of this book, the question of why technology did evolve at such different rates on different continents. Where do innovations actually come from? For all societies except the few past ones that were completely isolated, much or most new technology is not invented locally, but is instead borrowed from other societies. The relative importance of local invention and of borrowing depends mainly on two factors: the ease of invention of the particular technology and the proximity of the particular society to other societies. Some inventions arose straightforwardly from a handling of natural raw materials. Such inventions developed on many independent occasions in world history at different places and times. One example, which we have already considered at length, is plant domestication, with at least 9 independent origins. Another is pottery, which may have arisen from observations of the behavior of clay, a very widespread natural material, when dried or heated. Pottery appeared in Japan around 14,000 years ago, in the Fertile Crescent in China by around 10,000 years ago, and in Amazonia, Africa's Sahel Zone, the US Southeast, and Mexico thereafter. An example of a much more difficult invention is writing, which does not suggest itself by observation of any natural material. As we have seen, it had only a few independent origins, and the alphabet arose apparently only once in world history. Other difficult inventions include the water wheel, rotary quern, tooth gearing, magnetic compass, windmill, and camera obscura, all of which were invented only once or twice in the Old World and never in the New World. Such complex inventions were usually acquired by borrowing, because they spread more rapidly than they could be independently invented locally. A clear example is the wheel, which is first attested around 3400 BC near the Black Sea, and then turns up within the next few centuries over much of Europe and Asia. All those early Old World wheels are of a peculiar design, a solid wooden circle constructed of 3 planks fastened together, rather than a rim with spokes. In contrast, the sole wheels of Native American societies, depicted on Mexican ceramic vessels, consisted of a single piece, suggesting a second independent invention of the wheel, as one would expect from other evidence for the isolation of New World from Old World civilizations. No one thinks that that same peculiar Old World wheel design appeared repeatedly by chance at many separate sites of the Old World within a few centuries of each other, after 7 million years of wheelless human history. Instead, the utility of the wheel surely caused it to diffuse rapidly east and west over the Old World from its sole site of invention. Other examples of complex technologies that diffused east and west in the ancient Old World from a single West Asian source include door locks, pulleys, rotary querns, windmills, and the alphabet. A New World example of technological diffusion is metallurgy, which spread from the Andes via Panama to Mesoamerica. When a widely useful invention does crop up in one society, it then tends to spread in either of 2 ways. One way is that other societies see or learn of the invention, are receptive to it, and adopt it. The second is that societies lacking the invention find themselves at a disadvantage vis-à-vis the inventing society, and they become overwhelmed and replaced if the disadvantage is sufficiently great. A simple example is the spread of muskets among New Zealand's Maori tribes. One tribe, the Ngakui, adopted muskets from European traders around 1818. Over the course of the next 15 years, New Zealand was convulsed by the so-called musket wars, as musketless tribes either acquired muskets or were subjugated by tribes already armed with them. The outcome was that musket technology had spread throughout the whole of New Zealand by 1833. All surviving Maori tribes now had muskets. When societies do adopt a new technology from the society that invented it, the diffusion may occur in many different contexts. They include peaceful trade, as in the spread of transistors from the United States to Japan in 1954, espionage, the smuggling of silkworms from Southeast Asia to the Mideast in AD 552, emigration, the spread of French glass and clothing manufacturing techniques over Europe by the 200,000 Huguenots expelled from France in 1685, and war. A crucial case of the last was the transfer of Chinese papermaking techniques to Islam, made possible when an Arab army defeated a Chinese army at the Battle of Talas River in Central Asia in AD 751, found some papermakers among the prisoners of war, and brought them to Samarkand to set up paper manufacture. We saw that cultural diffusion can involve either detailed blueprints or just vague ideas, stimulating a reinvention of details. While the preceding chapter illustrated those alternatives for the spread of writing, they also apply to the diffusion of technology. The preceding paragraph gave examples of blueprint copying, whereas the transfer of Chinese porcelain technology to Europe provides an instance of long, drawn-out idea diffusion. Porcelain, a fine-grained, translucent pottery, was invented in China around the 7th century AD. When it began to reach Europe by the Silk Road in the 14th century, with no information about how it was manufactured, it was much admired, and many unsuccessful attempts were made to imitate it. Not until 1707 did the German alchemist Johann Böttger, after lengthy experiments with processes and with mixing various minerals and clays together, hit upon the solution and established the now famous Meissen porcelain works. More or less independent later experiments in France and England led to Sèvres, Wedgwood, and Spode porcelains. Thus, European potters had to reinvent Chinese manufacturing methods for themselves, but they were stimulated to do so by having models of the desired product before them. Depending on their geographic location, societies differ in how readily they can receive technology by diffusion from other societies. The most isolated people on Earth in recent history were the Aboriginal Tasmanians, living without ocean-going watercraft on an island 100 miles from Australia, itself the most isolated continent. The Tasmanians had no contact with other societies for 10,000 years and acquired no new technology other than what they invented themselves. Australians and New Guineans, separated from the Asian mainland by the Indonesian island chain, received only a trickle of inventions from Asia. The societies most accessible to receiving inventions by diffusion were those embedded in major continents. In these societies, technology developed most rapidly because they accumulated not only their own inventions but also those of other societies. For example, medieval Islam, centrally located in Eurasia, acquired inventions from India and China and inherited ancient Greek learning. The importance of diffusion and of geographic location in making it possible is strikingly illustrated by some otherwise incomprehensible cases of societies that abandoned powerful technologies. We tend to assume that useful technologies, once acquired, inevitably persist until superseded by better ones. In reality, technologies must be not only acquired but also maintained, and that too depends on many unpredictable factors. Any society goes through social movements or fads in which economically useless things become valued or useful things devalued temporarily. Nowadays, when almost all societies on Earth are connected to each other, we cannot imagine a fads going so far that an important technology would actually be discarded. A society that temporarily turned against a powerful technology would continue to see it being used by neighboring societies and would have the opportunity to reacquire it by diffusion, or would be conquered by neighbors if it failed to do so. But such fads can persist in isolated societies. A famous example involves Japan's abandonment of guns. Firearms reached Japan in AD 1543 when two Portuguese adventurers armed with harquebuses, primitive guns, arrived on a Chinese cargo ship. The Japanese were so impressed by the new weapon that they commenced indigenous gun production, greatly improved gun technology, and by AD 1600 owned more and better guns than any other country in the world. But there were also factors working against the acceptance of firearms in Japan. The country had a numerous warrior class, the samurai, for whom swords rated as class symbols and works of art, and as means for subjugating the lower classes. Japanese warfare had previously involved single combats between samurai swordsmen, who stood in the open, made ritual speeches, and then took pride in fighting gracefully. Such behavior became lethal in the presence of peasant soldiers ungracefully blasting away with guns. In addition, guns were a foreign invention and grew to be despised, as did other things foreign in Japan after 1600. The samurai-controlled government began by restricting gun production to a few cities, then introduced a requirement of a government license for producing a gun, then issued licenses only for guns produced for the government, and finally reduced government orders for guns until Japan was almost without functional guns again. Contemporary European rulers also included some who despised guns and tried to restrict their availability. But such measures never got far in Europe, where any country that temporarily swore off firearms would be promptly overrun by gun-toting neighboring countries. Only because Japan was a populous, isolated island could it get away with its rejection of the powerful new military technology. Its safety and isolation came to an end in 1853, when the visit of Commander Perry's U.S. fleet bristling with cannons convinced Japan of its need to resume gun manufacture. That rejection, and China's abandonment of ocean-going ships, as well as of mechanical clocks and water-driven spinning machines, are well-known historical instances of technological reversals in isolated or semi-isolated societies. Other such reversals occurred in prehistoric times. The extreme case is that of Aboriginal Tasmanians, who abandoned even bone tools and fishing to become the society with the simplest technology in the modern world. Aboriginal Australians may have adopted and then abandoned bows and arrows. Torres Islanders abandoned canoes, while Gawa Islanders abandoned and then readopted them. Pottery was abandoned throughout Polynesia. Most Polynesians and many Melanesians abandoned the use of bows and arrows in war. Polar Eskimos lost the bow and arrow and the kayak, while Dorset Eskimos lost the bow and arrow, bow drill, and dogs. These examples, at first so bizarre to us, illustrate well the roles of geography and of diffusion in the history of technology. Without diffusion, fewer technologies are acquired and more existing technologies are lost. Human technology developed from the first stone tools, in use by 2.5 million years ago, to the 1996 laser printer that replaced my already outdated 1992 laser printer and that was used to print this book's manuscript. The rate of development was undetectably slow at the beginning, when hundreds of thousands of years passed with no discernible change in our stone tools and with no surviving evidence for artifacts made of other materials. Today, technology advances so rapidly that it is reported in the daily newspaper. In this long history of accelerating development, one can single out two especially significant jumps. The first, occurring between 100,000 and 50,000 years ago, probably was made possible by genetic changes in our bodies. Namely, by evolution of the modern anatomy permitting modern speech or modern brain function, or both. That jump led to bone tools, single-purpose stone tools, and compound tools. The second jump resulted from our adoption of a sedentary lifestyle, which happened at different times in different parts of the world, as early as 13,000 years ago in some areas and not even today in others. For the most part, that adoption was linked to our adoption of food production, which required us to remain close to our crops, orchards, and stored food surpluses. Sedentary living was decisive for the history of technology because it enabled people to accumulate non-portable possessions. Nomadic hunter-gatherers are limited to technology that can be carried. If you move often and lack vehicles or draft animals, you confine your possessions to babies, weapons, and a bare minimum of other absolute necessities small enough to carry. You can't be burdened with pottery and printing presses as you shift camp. That practical difficulty probably explains the tantalizingly early appearance of some technologies, followed by a long delay in their further development. For example, the earliest attested precursors of ceramics are fired clay figurines made in the area of modern Czechoslovakia 27,000 years ago, long before the oldest known fired clay vessels from Japan 14,000 years ago. The same area of Czechoslovakia at the same time has yielded the earliest evidence for weaving, otherwise not attested until the oldest known basket appears around 13,000 years ago and the oldest known woven cloth around 9,000 years ago. Despite these very early first steps, neither pottery nor weaving took off until people became sedentary and thereby escaped the problem of transporting pots and looms. Besides permitting sedentary living and hence the accumulation of possessions, food production was decisive in the history of technology for another reason. It became possible for the first time in human evolution to develop economically specialized societies consisting of non-food producing specialists fed by food-producing peasants. But we already saw that food production arose at different times in different continents. In addition, as we've seen in this chapter, local technology depends, for both its origin and its maintenance, not only on local invention but also on the diffusion of technology from elsewhere. That consideration tended to cause technology to develop most rapidly on continents with few geographic and ecological barriers to diffusion, either within that continent or on other continents. Finally, each society on a continent represents one more opportunity to invent and adopt a technology, because societies vary greatly in their innovativeness for many separate reasons. Hence, all other things being equal, technology develops fastest in large productive regions with large human populations, many potential inventors, and many competing societies. Let us now summarize how variations in these three factors, time of onset of food production, barriers to diffusion, and human population size, led straightforwardly to the observed intercontinental differences in the development of technology. Eurasia, effectively including North Africa, is the world's largest landmass, encompassing the largest number of competing societies. It was also the landmass with the two centers where food production began the earliest, the Fertile Crescent and China. Its east-west major axis